Hi, today in classical mechanics we will start to see a new chapter, dynamics of system of particles. But first we have to see maybe the elementary section of center of mass. In Physics 101 we have seen the concept of center of mass, of a group of particles. And let me first write the definition for a group of particles. As you remember from 101, X center of mass was defined by the ratio of two sums. For instance, I is equal to 1 to n. Again, I is equal to 1 to n. Here we had, let's say, mi, xi. Here we had only mi, I from 1 to n. If you have a group of particles distributed maybe randomly, maybe uniformly, having different masses at different coordinates, we can find, for instance, if we have different objects m1, m2, m3, m4, m5 at different positions. First one is, let's say, x1, y1. The other one is x2, y2. Third one is x3, y3, etc. Then we have such a definition for the overall center of mass of the system of particles. And of course, similarly, we have an equation for the y center of mass. Then y center of mass is we just replace x with y, that's all, because x and y axis can be chosen arbitrarily in space on a certain plane. So according to your choice of x and y systems, you can find the general center of mass along the x-axis and also along the y-axis, and the intersection corresponds to the general overall center of mass of the system. So of course here we have a summation by summation from 1 to n, mi, not xi but yi. And here we have mi. Of course there is no possibility of cancellation of these mi's before taking the sums, etc. But this is very trivial. We have seen it in Physics 101 lectures. Today, of course, in classical mechanics, we will not be dealing with such relatively elementary topics, but let's find the center of mass of its general center of mass of a single object. But if there is symmetry, it is quite easy. For example, if you have a ball, for example, if you have a ball, from spherical symmetry, it is obvious that the center of mass is at the center. If you have, let's say, something like a circle, for instance, then again it is obvious that for such a circle, for instance, a ring, the center of mass corresponds to the center. However, there may not be any particle there. Just like in this case, because if you have different particles, maybe the overall center of mass turns out to be this position where there is no object. If you talk about an object, uniform object or non-uniform, as we will see, also the symmetrical or non-symmetrical, asymmetrical. So in such cases, the things may become a bit more difficult because these summations will turn into integrals in those asymmetrical cases, especially. For example, for a sphere or disk, if you see a disk like this, then if it is also uniform, so the center of the disk also is the center of the mass of the system. Or if it's a three-dimensional sphere, a ball, for instance, maybe solid ball, maybe spherical shell, again it is expected to have a center of mass at the center of the object. But if you have something not so symmetric, for example, a semicircle, as we will calculate, half of a disk, or a hemisphere. What if we have a semicircle or hemisphere? Because in those cases, for example, we have a semicircle. It is like a half of a disc, for instance. So this is the shape. So it is a half of a disc, and of course it is expected from the horizontal symmetry. It is expected to be somewhere along this dashed dotted line. But exactly where? At which position along this radius? So in order to calculate that, we need an integration, because these sums are now turned into two integrals. Of course, if it is uniform, if it's a uniform object, uniform means in this case having the same density overall, everywhere. Same density, surface mass density or volume mass density everywhere. Then it is, the denominator is simply the mass of the object. Maybe it is just a capital M. However, this part now becomes an integral that we have to calculate. Alright, if we have such a again, let's say we have a semicircle, such as half a disc, half of a disc, or a hemisphere. We take again, let's say uniform, because if it is also non-uniform, then we would have to take the denominator, find the denominator as a result of another integral, as we will do in some cases today. So here, of course, from symmetry, it is again understood and expected that the center of mass of this hemisphere, half of a sphere, is somewhere along this radius, but exactly where? Of course, it is not expected to be at halfway, because if you look at it, it is not a cube. If it were a cubic object, of course, the center, for a square, for instance, if we have a square, the intersection of the diagonals, this point corresponds to the center of mass. And here, it is not a cube. If it were a cubical object, of course, the center of mass would correspond to midway between the top surface and the bottom surface. And if A is the side length of this cubical object, it would be, this part would be A over 2, this part would be A over 2. Again, horizontally also A over 2, and in the y direction A over 2, etc. But this is not a cube, it is not a uniform object. It is a uniform object, but not a cube. So that we start now with solving the center of mass of a, let's say, half of a disc, for instance, but uniform. Example, calculate the position of the center of mass of a uniform object in the form of half a disc of radius r and mass m. Mass that doesn't have to be given, but let's give it also. So we have this picture and we just put it on the board on a certain xy plane. So this is the xy plane, and we have the semicircular object. It is filled. It is not a half of a ring. So we don't have a ring here. If it were a ring, the calculation would be a bit different maybe. This is half of a disc. So that this object, we take a disc, cut it into two, and we take one half and try to find the center of mass along this vertical radius. It is obvious from symmetry that it will never be anywhere outside this y-axis. So this is y-axis, x-axis. From symmetry, it is obvious that it is somewhere along the y-axis. uniform symmetry, it is expected to be, the center of mass is expected to be, the center of mass is expected to be along the y-axis. Along the y-axis. So it is never expected to be somewhere outside the y-axis. But now let's find the position along the y-axis. Y center of mass. So y center of mass. Now in the definition that I've written here, the integral, the sum now turns into an integral. So in the integral we have the positions and the mass elements. How do we separate them? How do we divide it into pieces? Here it seems that we have to divide it into horizontal strips, pieces like this. For instance, let's say this is one such mass element. So this is a mass element. What are the characteristic parameters of this? And this quantity from the x-axis is y, and this quantity is x, and the thickness is, what is it? It is dy. And it has a mass, let's say, dm. This horizontal strip, we divide it into a large number of, maybe 1 million pieces, so that we get a better and better result. We divide it into a large number of horizontal strips having length, because this is, remember, radius r. This is radius r. This is also radius r. Having length 2x, strips having length 2x, 1x on one side, the other x on the other side, because it's symmetrical division. Having length 2x, thickness means width here, width and thickness here means the same. So thickness dy and mass dm. Having length 2x, thickness with dy and mass dm. All right. How do we write this integral now? It is position of this, any of these strips, let's say y, times dm, divided by all mass m. Because there is no need for to integrate the denominator. It's a uniform object already, and the mass is already given. Even if it isn't given, you can assume it is a certain mass m. Anyway, it will cancel at the end if you do the calculations correctly. Alright, how do you write dm now? So we need just like surface charge distributions. Please always keep in mind that the mass distributions and charge distributions in electrical topics are quite corresponding things. For example, if there were a charge distributed uniformly, and we want to find the charge contained in this strip, we would multiply the general overall surface charge density sigma by this area, so that dq charge within this strip only, dq would be sigma times this area. So we have, let's consider this area. This is the object. That part is 2x. This part is dy. So the area dA is simply length times width, 2x times dy. And dm is simply sigma times dA, because sigma is the surface charge and mass density are quite parallel things. So surface mass density sigma is simply dm over dA. So dm, the small mass contained within this horizontal strip, is sigma times dA. How do we write sigma? Since it is a uniform object, it is uniform. If it were not uniform, you would also, as we will do in the next examples, you will also have another integral. But this is relatively easier. So dm, sigma is just simply mass over total area. What is the area of that semicircle? Pi r squared over 2. So this is pi r squared will be the full surface area divided by 2. So that sigma is 2m over pi times r squared. So let's continue here with this simple integral. This y center of mass is now found as y value, alright, dm. What is dm? Sigma times dA. dA is 2 times x and dy divided by the total mass m. Now there should be only one variable of integration, x or y, but not both. So we should express for instance x in terms of y, and the limits of y will be let's write the limits here, y equals 0 to y equals r. So these are the lower and upper limits of integration variable y, but we should get rid of x in favor of y. How do we do that? Let's look at the picture now. If you construct a hypothetical right triangle, right? This is the right triangle. That hypotenuse is r, of course it's the radius. So then we have an expression x squared plus y squared equals r squared. So instead of x, we can write r squared minus y squared, but in root. So x is just the square root of this difference, as you easily expect. So let's continue with this substitution now. Let's take 2 sigma over m outside, they are constants. So we have y center of mass. We take this 2 sigma over m, 2 sigma over m outside because they are not variables. Inside the integration we only have x, y, dy. X, y, dy. But x is now replaced by this thing. So that, let's call this thing A now. Y, center of mass. Is this A multiplied by y times, inside we have r squared minus y squared, also we have dy. So it can be solved by more than one way. First way may be the easiest one, because if you separate it into 2 parts, y and the parentheses, if you call this part, for instance, as u, then du is minus 2y dy. We already have y dy, so by writing a minus 2, we can finish. One way. The other way can be another trigonometric substitution, which we need in the following hemispherical case. For this case, let's choose the easier one. Let u be r squared minus, but there's this root, of course. There is this 1/2, power of 1/2. Let u be this thing. Don't forget the power 1/2. Then du will be, just the inside. No, u is this, alright, u is this. So that du will be minus 2y dy. Do we have the right hand side? Yes, we have the necessary parts. Y dy we have. We don't have minus 2, so it is easy to multiply and divide by minus 2. So we have, first, y center of mass will be a integral y. Let me first write the first part, the remaining part. Let's go slowly. So y times u to the power 1/2 and dy. But we have already the necessary things y dy. So let's multiply by minus 2, divide by minus 2. So that it doesn't change. Then this thing, that part is simply du. So let's take minus 2 outside. We had an a divided by minus 2. Inside the integral we have u to the 1/2 times du. And we know what this will be at the end of integration. So that our new variable u becomes minus a over 2. So u to the 3/2 divided by 3/2. And the limits will be put here. But now we can go back to the variables that we started with. So let's cancel these 2's. So we have y center of mass minus a over 3. Then u. What is u? We set it to r squared minus y squared. R squared minus y squared now to the power of 3/2. And the limits are from y equals 0 to y equals r. So let's put these two limits and then subtract. So it is minus a over 3 multiplied. If you put r, you get nothing. So this is 0. If you put 0, this part drops, r squared. But squared and 2 cancel, r cubed. 0 minus r cubed. So these minus signs cancel. We have y center of mass equals plus now. These minus signs cancel after this 0. So a over 3 r cubed. So let's go back to substitute a. What was a? A was just 2 sigma over n. Finally, y center of mass is a over 3. A is 2 sigma over m. We also have a 3 in the denominator, so let's write it as 1/3 multiplied by r cubed. But what is sigma? Sigma was already, sigma was the ratio, remember, mass over pi r squared over 2. So 2m over pi r squared. So let's substitute that. 2/3, m is here. Sigma, what is sigma? 2m over pi r squared multiplied by the remaining r cubed. So there are cancellations. M's cancel and r squares cancel as expected because the result should be in terms of a length in terms of r. Some number times that, and that number of course should be less than 1. Necessarily it is somewhere inside the object. So we have 4 over 3 pi. So that y center of mass is 4 over 3 pi, which is nearly 4 over 9, a bit less than 4 over 9, 4 over 3 pi times the radius r. Since this quantity, 4 over 3 pi, is approximately, so y center of mass is approximately 4 over 9, a bit less than 4 over 9 r. Of course, it has to be something less than r. If you find anything more than half of r, it means we made a mistake. Because this object cannot have the center of mass at a position higher than half of the radius. Obviously, because there is no such, this part of the mass is missing. So obviously, it wouldn't be somewhere above r over 2. Of course, this quantity should necessarily be something less than 1/2. So it is indeed less than 1/2, 4 over 3 pi, along this value. So for example, if you divide it by 9 pieces, then 4 parts are here and 5 parts are there approximately. Very approximately, if you take pi as 3. So this is the expected result. Now let us apply this idea of division into strips to a case of a triangle. Find the center of mass of a right triangle of length A and height or width B. Length A, width B. Center of the uniform, let me add the word uniform, right? So let's place it on the xy axis. So this is the object. Right triangle and the length is A, the other dimension is B. And it is again very easy because we have to divide it into vertical, this time vertical strips. So let's divide these into vertical strips first to find x center of mass. Let us first find the x center of mass. Since it is uniform, the surface mass density is everywhere the same. So let the mass be m. Let its mass be m. Triangle, rather, let me write it here, of mass m. Of length A with B. Okay. So x center of mass is simply an integral divided by total mass m. What is that integral? Now we are interested in these. So that this strip has the length y and the thickness dx. So the area is y times dx. Therefore here we have x, and x is this component until this strip x so that we should multiply all x's by all such dm's. And as in the previous case, this strip has area, length times width. Length is y, width is dx. And dm, mass dm, is sigma times dA. What is sigma? Sigma is, at the end we can substitute mass over total area. Let's now use sigma until the end. Alright? And we just substitute this to x center of mass. In the integral we have an x. For dm we have sigma dA. What is dA? Y dx. Again we have a case where we have both x and y. So we should get rid of one in favor of the other. So we should reduce the variables to 1 in such kind of integrals. And in this case, since x takes value, of course y is also taking values, maybe the easier way is to get rid of y in favor of x. Let us express y in terms of x. And for this purpose we have a line. What is that line? We have this line. What is the equation of such a line? It is in the form of y is equal to, let's say, mx plus n type of thing. Since there's no intercept, it passes by the origin, there's no intercept n. But m is the slope, little m is the slope. What is the slope? Tangent theta, b over a. So m is, little m is not the mass, capital M is the mass. Little m is the slope of this edge of the triangle hypotenuse. So that it is b over a. A is this part, b is the height. So m is b over a. Now what do we have in this integral? X center of mass equals, let's take sigma outside, divided by m, so sigma over m are taken out. We have the integral. X remains there, x remains. Y is now written as, y, instead of y we write ba times x, b over a. So we have b over a times x, and don't forget this dx. So it is very easy to take this integral. The constants are sigma over m. We also take b over a outside. Inside we have x squared dx. Now the limits are from 0 to the end of this horizontal part, which is a. Therefore, it is the constants sigma b over m times a multiplied by x to the 3 over 3. Limits are from 0 to a. If you put this is a cubed over 3. If you put sigma as total mass, what is sigma? Total mass per total area. What is the area of a triangle, such right triangle? Length times height over 2, AB over 2. So here we have AB over 2. So 2 comes up. And here, x center of mass, sigma. What is sigma? Twice m over AB. Divided by b over ma. B is there, m and a are written. And for this integral part, we had a cubed over 3. So there are some cancellations. B's cancel, m's cancel. These two a's cancel, two of them. So we have 2/3 a as expected. Again, x center of mass is 2/3 a. So it doesn't depend on b. It is it depends only on a, provided that this is a line. If it were in the linear edge, for instance, like a square x squared, y equals x squared type of a parabola, then we wouldn't conclude that it is 2/3 from the beginning. Because that substitution would be something else in that case. What about the y center of mass? Is there any need to do it again? Because if you put it the other way, for instance, you can easily understand that. For the other case, if you put it, for instance, the other way, like this, so that this is the side B, that is the side A, we expect that it is 2/3 from the beginning. So if you divide it into 3 equal pieces, 2/3, and this is also divided into 2, so that this point corresponds to 2/3 A from this tip, 2/3 B from this tip, so that that point seems to be the overall center of mass of this triangular uniform piece. Now let's say one more case. This time the geometry is easier, it will be a rod, however the density will not be uniform and will be given according to a function. Another example. So we are given a rod. placed along the x-axis, so there is no y center of mass in this case. We only find one coordinate. Let's say this is the length A. Find the center of mass of a rod of first let's find the total mass. It is easier. A rod has length A and a linear mass density, just like the linear charge density in electricity, and linear mass density lambda is equal to some lambda 0 times x. Very simple function, because as we understand from this function, for very small values of x near 0 here, this is almost massless. For example, that rod can be prepared from different materials whose densities are gradually increasing from left to right. If you take some maybe pieces of paper, some polystyrene, etc., very light, very less dense materials, and from left to right you increase to, like, for instance, until lead, gold, etc., iron somewhere, in the middle maybe wood, etc. So plastics, ceramics, but from the very light materials, small density, to very high density materials, you can prepare this rod. In the first part, we will find the overall mass, total mass. What is it? Because it is not given. Only this function is given. And also, we will find the center of mass of this non-uniform object. A rod has length A and a linear mass density lambda 0 times, let's say, x over A. Because for small values, again, it is, if you don't write this A, the units do not match. So now lambda and lambda 0 have the same units, mass per unit length. So kilogram per meter, for instance. So you should multiply it by some fraction in terms of distances. So x, whatever x is from the beginning. So this is, for example, in the charge distributions, for instance, charge distributions, we use rather some dots to indicate how the charge is distributed. For example, near the origin, we have very rare points, and then those points become more and more frequent. According to this distribution, the density is very small, so it consists of very light, low density materials near the origin. As you go to the other end of the rod, density, linear mass density, becomes greater and greater. For instance, here we have some, let's say, some paper, some kind of paper, because even the papers do not have the same density for all types. Some kind of paper, for instance, some strips of paper or straw, and here maybe, let's say, lead or some other iron or other heavy metals, for instance. So you can prepare such a combination by pressing those pieces together. Alright, everyone is given in this form. A, find the total mass, and B, find the center of mass along the rod from the origin, of course. This is the origin of. Again, we divide it into small pieces, not strips, because this is already a one-dimensional object, but we will divide it into very small pieces of length dx. Part A, let us divide it mentally of course, let us divide it into a large number of infinitesimally small pieces. Infinitesimally small pieces of length dx. Of length dx of mass dm. So we have, let me draw the picture again. We have the rod, and let's consider one such piece. That piece is at the distance x from the beginning, because x is important. This function is given in terms of a, and it has a thickness dx, but no area. Since we don't have an area element, we have the length element, and therefore we have the linear mass density, not surface mass density. What is this dm? dm is of course lambda times dx, because lambda gives us the mass contained within a certain small part of length dx. Lambda is given by a function, so that m is integral dm. But this dm is written by lambda times dx. But what is lambda? It is already given. Lambda 0 times x over a multiplied by dx, starting from x equals 0 until x equals, let's say, a. Lambda 0 over a are taken, lambda 0 over a. Inside we have x dx, it becomes x squared over 2, x squared over 2, from 0 to a. So that total mass turns out to be lambda 0 over 2a multiplied by a squared minus 0. So these a's will also cancel. Lambda 0, total mass is lambda 0 a over 2. Lambda 0 a over 2. So this is the total mass in it. However, the center of mass, as you expect, does not correspond to midpoint. Obviously, it corresponds to somewhere beyond the midpoint because of this gradually increasing linear mass density. It is expected somewhere to the right of a over 2. If it were a different mass density, maybe it would be in the first half. But from this we understand that since that x is increasing from left to right, the overall center of mass corresponds to somewhere in the second half of the rod. And this time we have another integral, part b. Part b says x center of mass integral each x will be multiplied by the dm contained in it divided by the total mass, because we have already calculated this total mass and so we can substitute at the end. Now we are interested in the numerator, x dm. So x multiplied by dm, but dm was already defined as lambda dx. Lambda dx, but lambda is lambda 0x over a. Don't forget this 1 over m. So we have, let's take lambda 0 outside over m integral x. We also have another x dx. So a is also taken out. Lambda 0 over ma. Inside we have x squared dx. This becomes x cubed over 3. So lambda 0 over ma x cubed over 3, and the limits are from 0 to a again. Therefore, it is x center of mass will be lambda 0 a cubed over 3 divided by m, but m is lambda 0 a over 2. So as you write them, lambda zeros cancel, a cancels one of them. There's one more a. Yeah, let's not make a power mistake, because x is expected to be a length, something times a. So we have lambda 0 x over a. There's one x and another x squared, x cubed over 3, alright? So we have lambda 0 over m over ma over ma. And there's one more a here. There's one a, another a, so this cancels two of them. We have a single a. So x center of mass turns out to be, there is only one a, but 2 goes up. 2/3 a is the result. Again, this is a 2/3 behavior, just like the triangular problem, because the idea is similar. In the previous case, we had gradually increasing masses in each vertical segment strip. In this case, we don't have such strips. However, the density is increasing linearly in the same manner. That's why it is behaving in the same way. 2/3 from one end, lighter end, corresponds to the center of mass of this non-uniform rod. Now, after this introduction with the center of mass, now let's consider the linear momentum first. Linear momentum and impulse. Of course, these are the things that we have already learned in Physics 101. But just to refresh the memory, let's talk about it to some extent and then consider some examples. Of course, linear momentum is defined by, I will not go into the preliminary details of these concepts, but linear momentum, as we know, is the product of the mass and velocity of a particle, any object. And we also know the Newton's second law that we learned in Physics 101 again. But this law, we know, can also be written as the rate of change of momentum of an object. So force is in general m times a, but it is as dp by dt, or delta p by delta t. But p is, as we see, the product of these things. Normally, p is a product, it's a multiplication. So we have d by dt applied on m times b. So we have a product, it is like the product of two functions, for instance, f and g. If you want to take the derivative of this product, as we know in the very simplest form, f prime g plus g prime f, or fg prime. So derivative of one times the other itself plus the derivative of the other and the first one. So if you apply this time derivative, time differentiation on this product, what do we get? F is equal to dm by dt multiplied by v plus m times dv by dt, according to this simple rule for the differentiation of a product. But in general, in almost all the problems of Physics 101, we hold the mass as constant. So the mass of the particle, of the object, does not change during the whole motion. In general, in the simplest, relatively simple cases, the cases in Physics 101, for instance, elementary mechanics, the mass does not change. If you have a ball, it is always the same ball, for instance, moving. Or if you have a car, it is the same car. It doesn't lose or gain any mass, normally, in those cases. But now, in classical mechanics, let's be interested in a bit more complex cases where the mass is also changing. So if you don't have this first term, if you neglect this dm by dt, then you are left with f equals m times dv by dt. But dv by dt, as we know, is the acceleration. So it reduces to the equation f equals ma. But in the more general cases, it is not only m times a, but plus this term, dm by dt, coming from the change of the mass of the object multiplied by the velocity at that time. So rocket, for example, rocket motion, as we will see today in some rather elementary form, is one of such cases. because the masses of the object is at the beginning a certain value, let's say capital M, but during the motion in free space, it needs some maybe change in the direction of the motion, or it has to be moving maybe faster, maybe slower. So in order to realize those changes, some fuel is thrown back, maybe in the same axis, maybe a bit sideways, so that the object is changing direction, etc. So from now on, please be careful that F is not only m times a, but it also has a second term which comes from the probable change of mass in time and the velocity of the object. Alright, so F equals dp by dt is a more general expression than just F equals m times a, because in this case we already, it means we already assume that the mass does not change. But why not? Because in some other cases, mass of the object, moving object, may change as well. So what about impulse? Whether or not mass is changing or remaining the same, F is equal to delta p by delta t. But you can write it as, for instance, F delta t equals delta p. And also delta p is m times delta v in case that m remains constant. So this is the new way of writing it is F delta t is equal to m delta v. So this is another form of writing it. But both sides, whether we have F delta t or m delta v, it has also a special name which is called impulse. So this thing is called impulse. It is generally represented by capital J. So we can find the impulse of an object maybe hitting a surface, hitting another object, for example. If you take a ball and send it to a wall, for example, during the, let's say this is the wall, and we have a certain spherical object, ball for instance, moving at the beginning, it has such a velocity vector, it, let's say, let me call it V1, for instance, V1. When it comes here, this is a kind of slow motion analysis. So this is also moving at some V1, but then it is slowed down, so it is still moving with some V2, which is less than V1, and then it stops momentarily. So V is equal to 0, but then it is reflected back as expected. So the symmetrical case is just this one. It is still in contact and now has this velocity minus V2, just the symmetric case, but still in contact with the wall. And finally, this is the case where it just leaves it with the negative velocity minus V1. So this is the very short time, it takes a very short time interval, of course. This takes maybe delta t. This is maybe 0.01 second, 1% of a second. For example, if you take a ball and throw it to a wall, for example, a surface, the impulse, the contact time is almost maybe 1% of a second. So whatever is happening in that small time interval. And we also know that from statistical physics, for example, we have a concept of pressure. What is the pressure of a gas? The gas molecules are continuously hitting the walls of the container, whether it's a glass container of this size or it is the room like this. The gas molecules, air molecules are continuously hitting the walls, and each small molecule is hitting the wall just like this collision and is reflected back. Of course, it doesn't have to hit it perpendicularly. It may collide with the wall at any angle, but also the incident angle and the reflection angle are the same. Okay, this may be just a simple gas molecule, hydrogen gas for us, or any other gas. This molecule, in this simple case, we assume that it hits the wall, this vertical wall, just perpendicularly. Of course, it doesn't have to, because maybe if this is the angle of incidence, then the other is just like the reflection of light from a surface, from a mirror, for instance. So this angle is, let's say, theta. This angle is also theta, so that momentum is conserved, and this kind of collisions form the pressure of this gas. Because during this collision, what happens, according to this expression, m delta v, this object has mass m. It is moving with some velocity v1, but delta v is minus v1 minus v1. Or what is the change? v1 minus v1. So the change is in fact twice v1, or what velocity it had. So the change in the velocity is almost twice. Of course, if you have an angle other than, let's say, 90 degrees, or in this case, other than 0, if it is the angle with the perpendicular axis, then of course the change will be something less than twice. But in the greatest possibility, it is whatever v it had at the beginning, and in the reflection it has just the opposite value, so twice. Therefore, this impulse consists of these two terms: mass of the object times the change in its velocity. But during the same contact period, what happens also can be seen from the left-hand side of the equation. During a certain delta t, which is almost this much, very short time interval, a force occurs. But that force is two ways. This is both the force that the particle exerts on the wall and the force that the wall exerts on the particle. And since in the pressure we are interested in the force exerted by the particles on the walls of the container, pressure occurs as a result of the sum of these forces. Of course, these molecules are very tiny particles, having a mass of 10 to the minus 25, 27, whatever, kilograms. But the number is huge. The number is very, very high. Number of particles per unit volume is quite high. So you multiply an astronomically large number by a very small number, so the result is a normal number, not very large, but the pressure is necessarily because of these interactions of the particles with the walls of the container. Whether the container is a small vessel, glass vessel, for instance, or a thermos bottle, or a very large hole, for example. Okay, so the pressure, as I said before, arises from such interactions. And the impulse is, we can look at both sides, is the applied force of the walls of the container on the particles, or vice versa, the force exerted by the particles on the wall during a very short time interval, delta T. But during, for the case of a gas, for instance, during a small delta T interval, there are some number of particles which are hitting the walls. But a bit later, there is one other delta T, because some particles are still flying inside the room, but some percentage is hitting. But the ones that are hitting the walls now are then moving freely between the walls in the air, in space. But some other particles which were initially flying in the air are now hitting the wall, etc. So statistically, that average number is just making some fluctuations around a certain average. But we are in this course not interested much in what the gas molecules are doing, but this is the idea. The idea of pressure comes from the interactions of these molecules with the walls. So, for example, let's say we have some card like this. Okay. So very simple cart that you use in shopping, for example. But assume the sides are closed by some closed surfaces. So by, for instance, throwing some balls, 1, 2, 3, etc., by continuously throwing some tennis balls or larger balls, basketballs, for example, by throwing some, sending some beam of basketballs, for instance, to this object, you can manage to move it. Okay? If you send these, let's say, basketballs or any other sufficiently massive particles as a beam onto this surface, then this object, this card, may start to move by some velocity v0. This is the reason of this, the reason comes from this equation, because if you send those particles, those balls, and each ball hitting the wall then falls down, so it loses momentum in the horizontal sense, in the x-axis. Therefore, for example, if each ball has a mass little m, but the card has mass capital M, for example, so each one moving with some initial velocity v0 loses after the collision and falls vertically down by assumption, or is reflected with a speed less than the magnitude is less than v0, for example. So anyway, it loses some part of its momentum in this collision. Then that momentum is imparted to the card. So as a result, if the friction, for example, is not too high, then this card may start to move forward because of this equation. So this is the main idea of momentum and momentum conservation. Why do we have momentum conservation? Let's consider this equation again. F equals delta P by delta T. And this F comes from the external forces. External in the sense that if you have a system, you can specify your system, for example. You can isolate your system from environment, and any force, any interaction coming from outside is called F external. So F external is the force that causes the momentum of the object to change. So if there is no F external, momentum does not change. Momentum, whether it is 0 at the beginning or some positive number, it remains the same. If F external is simply 0, then what happens to the right hand side? Delta P is also 0. But delta P is the change of momentum between, let's say, Pi and Pf. Pi minus Pf will be 0. So it means P initial is equal to P final. So that it is the conservation of linear momentum. Angular momentum we will consider in the other lecture. So this is the conservation of momentum. If we have the condition satisfied, what the condition? F external is just 0. And then there's some kind of exchange between the elements of the system, just like the famous example that we were solving in Physics 101, for example. I will not solve it, but just remind you. Here we had a sort of boat, for instance, and there was a person on it at the back. And what happens when that person walks to the front of the boat? So, in a very exaggerated manner, let me draw the person here. So, I will not write the steps, but just remind you the idea. If this person having mass little m and this boat having mass capital M are initially at rest, and that boat is just touching the quay, the platform on the shore. So if this person is walking to the front part of the boat, then what happens? The boat is moving, shifted a bit backward because of the relative motion. What is the physical reason for this? There is no external force because we define the system as composed of boat plus person. And anything from outside will be called F external. However, there is no force acting on the system from outside. So F external is 0. Therefore, momentum, which is initially 0, should also remain as 0. However, we are not interested in the velocities in this problem, but since there is no change in the velocity, which is already 0, the center of mass of the system, wherever it is, should remain there. This is the physical idea. And we don't know the exact position of the center of mass, of course, but it is not difficult to define it anywhere, such as the midpoint of the boat, etc. And we solve it. At the end, we understand this x, what that shifting part should be. Of course, when the person turns back and walks again to the rear of the boat, we turn back to the initial situation where the boat is just touching the quay. So this is the idea of conservation of momentum. Also, for some sled moving, sliding on frictionless ice, if there's a person at the back and walks towards the front, of course that walk causes the sled to lose some speed because of, for example, let me consider, I've not solved it, but just remind you again, this is the beginning, so there's a sled and a person here. Person has mass M, sled has mass capital M. This is frictionless ice. And that is the sled sliding freely on frictionless ice. Assume that this is at the beginning moving at some speed v0. But then, on the course of the motion, for example, here at a certain later time, the person is walking from the back of the sled to the front part. By some velocity v person, for example, some little velocity vp. During the motion, as the person is still walking, because walking means pushing the ground backward with your feet so that you move forward with respect to the ground, whether the ground is at rest or the ground, even the ground is moving. Okay, so this is now moving with the speed v1, but that v1 should be less than v0 because of the walk in the same sense as the sled. But then, after a while, for example, the person arrives at the front, etc. But then, assume that the person is now walking backward with some negative v person. In that case, the speed of the boat will be, let's say, v2 will be greater than v0. Initial value was v0. When the person and sled are moving in the same sense, the speed of the sled is a bit decreased. Of course, proportional to the mass, of course. A very heavy person and a very light sled may cause a considerable drop in the velocity, and conversely, as the person is walking backward, so the two velocities are in opposite senses. Here, Vp is in the positive x, velocity of the sled is also in the positive sense, then this new velocity is a bit less than that. But if they are in opposite senses, negative Vp for the person, but sled is still moving in the positive x, then the velocity of sled is greater than a bit, at least, the initial velocity v0. So this is the main idea of momentum conservation, because if you can choose any reference frame you like, you can choose a reference frame, y-axis is not important, but you can choose an x-axis, for instance, and an observer. This observer may stay outside and look what is moving in front of him, according to that observer, or you can choose an observer moving with the sled, a second person who is at rest with the sled, or a person, for instance, moving at the center of mass of this sled. These are all possibilities, but you should write your equations accordingly in each case. And the impulse, let me repeat, impulse J is F delta T or M delta V if something is colliding with something else and during a certain generally short amount of time. Now let's consider an example example on this topic, on impulse, for instance. So let's try to solve it. A chain, a uniform chain of mass m, length b, is hanging vertically and at rest. The lowest tip, or the lower tip, just touches lower tip or lowest buckle just touches the ground, as shown. So for example, this is the ground, and this chain, upper position, this is the long chain, uniform, consisting of several buckles, rings, but the lowest part, this point, just touches the ground without any applied force between them. And that length is B, as mass m, little m. Then what happens? Then it is released. The upper end is released. The upper end find the weight or find the force F exerted by the ground on the chain, or by the chain on the ground, exerted by the chain on the ground when the upper end falls a height y. When the upper end falls a length y. So the first part is easily drawn like. What about the second part? Here some distance is, that part is missing. So it is falling down and some part is already accumulated. So this part, let's say y, from the initial level, the uppermost buckle has fallen a distance of y, and it is still, of course, moving down with some velocity. And since it is something which is not extensible, all the buckles, all the small pieces, rings, are moving with the same velocity v. And the one here, even the one lowest one, is hitting the ground with velocity v, but comes to rest almost immediately. And this part, the missing part, has accumulated already on the ground, on the table. So what is the force applied by the ground on the chain? Or I say, what is the force applied by the chain on the ground? You can also call it this way, because this is a two-way interaction. Now it is obviously understood that this force consists of two parts. One is the weight of the part which is already accumulated. So weight of this part is now acting on the ground, on the table. But this is not all. Even the more important part is the second part, which is the impulsive part, because of these collisions every time. In even a very small time interval dt, new and new, continuously further and further particles, small buckles, rings, are colliding with the ground and coming to rest. So now the linear mass density is necessary here. The linear mass density lambda. Since it's a uniform chain, we simply divide the mass by the length. Lambda equals total mass m, little m, divided by total length p. So this is lambda. Then what is the mass which is missing here? So because it is this part, as we said, is already accumulated on the ground. So F1. Then F1 is simply mass of this part times g. What is that mass? Lambda times this length y. So the first part of the force is lambda times y multiplied by g, because this is just the mass m1. Mass m1 is just the mass of this missing part, which is already accumulated. So what about the other part? The other part requires a bit more attention, because we have to find the velocity also. At this moment, all the pieces are falling with the same velocity. At that moment means when that length is y. At the moment when the upper end is at a distance y below the initial level, at the moment when this is lower than that, all the pieces are falling with some velocity v, and it is easy from energy conservation. From that level, all the pieces are falling at velocity v, at the same velocity, of course, at the same velocity v. What is that velocity v? From energy conservation, from physics 101, we can easily find what it is. So this part, for example, when something because each piece can be considered separately, independently. Any particle, once it is there and now it is there. So that from energy conservation, m times g times y, this has, let me call it m prime, for instance. It doesn't get confused with the total mass. This m prime, anything, is 1/2 that m prime v squared. So cancelling these m primes, v turns out to be 2gy, because even if it's a single, whether it's a single piece of chain or the full chain, when the object is falling down and it has left the initial position by a distance y, its linear velocity is √2gy. This is obvious. Alright, then we consider a small part of it. For example, this small part. What is that small part? It has a mass dm. dm consists of a very small mass element. dm is equal to what? Lambda times, or in other words, it is v times, first it is lambda times dy. Length, linear mass density, times that small length. This distance is dy, but the mass contained is dm. So this dm, mass of this small piece, is the product of the overall density times this short length, dy. But dy, what is it? Dy is simply velocity and dt, because that distance is covered by any particle with the velocity v in a time dt. will be found as follows. F2, which is the impulsive force, F2 is just delta B by delta T, or dP by dt. Is just change in the momentum during a very small time interval dt. And during this dt, that part, that much mass is falling and immediately coming to rest, so that the change in momentum is 0 minus this much, because final value vertically of the momentum is 0. Therefore dP, what is dP? It is mass times velocity. But which mass, which velocity? dP is simply mass, it is dm. Velocity, it is v. During a time interval, dt. V is there. dm is, what is dm? dm is lambda dy. dm is, and dy is simply v dt. Therefore, F2 is v times dm by dt. V times, what is dm? It is lambda dy. Lambda dy by dt. But what is dy? It is v dt. So let me replace dy by this v dt. Therefore, F2 turns out to be v times lambda times v dt divided by dt. So we have, after cancellation of the dt's, we have lambda times v squared. But v squared was already found as 2gy in the vertical sense. So it is simply lambda times 2gy. There is one lambda gy, but plus 2gy. Totally, F is equal to F1 plus F2, and F1 is just lambda gy, the other is 2 times lambda gy. So it is totally 3 times lambda gy. What is lambda? It is the linear mass density. 3 times lambda is total mass m by total length v, g times y. So the mass is, that part, F is 3 times, because this part is just the mass of the collected part, accumulated part. It is 3 times that. F is 3 times the weight of the accumulated part. So this is quite interesting, huh? So what is, let's consider some numerical values. For example, let's consider here, this is quite an important conclusion. For example, let's say this is the upper position. Now, this is the moment where that height is y from the initial upper end. Alright, let's say this is totally 100 kilograms. It's a long rope, not a rope, a long chain, 100 kilograms. So, of course, we have to multiply by G 1000 newtons, etc. But let's consider only the mass, for example, without G, and assume that 1/10 has fallen. Alright? So that part corresponds to 10 kilograms. 1/10. So Y is equal to, for instance, total length over 10. So that, for instance, total length is whatever it is, but total mass is, let's say, 100 kilograms. Since only 1/10 of it has fallen, this part has a weight of 1, which is just 10 kilograms. First part. But second part is more than that. Second part is corresponding to 20, of course force is not kilogram, but F1 corresponds to 10 kilograms, F2 corresponds to 20 kilograms. So totally, although the mass lying on the surface corresponds to the mass of 10 kilograms only, it is as if there are 30 kilograms of the chain. So let's continue in the falling motion. Then new buckles are also falling down until the end, very last piece is just hitting it. So there are almost all the chain is lying. What is the total mass? 100 kilograms. What is the force caused by this interaction? It is almost 300 kilograms. Almost. Until the last one stops. When the last one is also falling and comes to rest, of course the total value is indeed corresponding to 100 kilograms. But until the end, last one is hitting the ground, that accumulated part has a mass of almost 100 kilograms, but the value here, the force between the two pieces, the chain and the table, is 3 times that, as we see here. And the impulsive part is twice the weight of the accumulated part. This is something important in maybe practical cases. For example, the strength of this surface may not be sufficient to withstand the falling mass. It can withstand maybe only 115 kilograms. However, until the last one is hitting the ground, the total force acting between the surface and the chain, or chain and surface, is almost 3 times the weight of the accumulated part. 1 comes from the weight of the real accumulated part, and 2 comes from the impulsive force necessary to stop the falling pieces of new pieces of the buckles. Now let's have another example where some mass is transported from one object, one car, to the other car. There are 2 railway cars, for instance, having the empty masses M1 and M2. Also, the upper one is filled with some sand or water. Let's choose sand, for example. So that sand is transported from the upper one to the lower one. Initially, lower one is at rest. Let me write it. Masses are M1, M2. There are 2 railway cars. One above the other. Above means they are moving at different rates. One moving in a rail above the other. The upper one has mass M1 is moving at velocity v1. The lower one is empty, has mass M2 and is at rest. So from the upper to the lower, sand is transported. From the upper to the lower, sand or water or any other material, from the upper to the lower, sand is continuously transported at the rate of, let's say, beta, is continuously transported at a rate, let's say, beta. Beta corresponds to dm by dt. So we understand that beta is the rate of falling mass. So beta is units of kilograms per second. So in 1 second, let's say, 10 kilograms of sand are transported vertically. Transported at the rate beta vertically. Assuming the sand has not finished yet, assuming the sand is still flowing, the sand is still flowing, find the velocity of the lower car, V2. Find the velocity of the velocity V2, because it was already at rest initially. Assume the sand is still flowing down, find the velocity V2 of the lower car at time t, because at time t equals 0, the sand is started to flow down. So this is the problem. It's a kind of conservation of momentum. Are we sure that we can apply conservation of momentum? Yes, we can apply it because there is no horizontal force applied. So what is happening in fact is this. There is an upper car. Let's look at it in the sideways. And the lower car. Since here the sand is flowing continuously, since there is no horizontal force applied on the upper car or on the lower car, there is no horizontal force on either. Since there is no horizontal force applied, the momentum of the system is conserved. What is the system? System now consists of these two cars. This is our system. And as you see, there is no horizontal force applied on the system from outside. So the momentum in the horizontal sense is necessarily conserved, assuming no friction. Alright, since there is no horizontal force applied, the momentum, of course we talk about linear momentum, the momentum of the system, which is upper car plus lower car. The system consists of upper car plus lower car. The momentum of the system upper car plus lower car is conserved, which means P initial is equal to P final. But let's be more specific, not initial and final. P at time t equals 0 is equal to P at time t. What is the total momentum initially? Since the car is at rest at the beginning, there is no contribution from the lower one. Only the upper one. P at time t equals 0 is only upper car mass m1 velocity v1. These are already given. But what is P of t? It is Let me write it here. We need some more space. Momentum at time t. Until time t, some mass has already accumulated. What is that mass? We look at the rate, dm by dt, this in terms of some kilograms per second. Let's say in 1 second, 10 kilograms of sand are transported. In 40 seconds, we simply multiply 10 and 40, 400 kilograms. In 1 minute, for example, 60 tons and 600 kilograms. Assuming these are big cars, so they contain maybe tons of sand, and they are sufficiently long, so although they are moving, they still find some time to send the pieces of sand downward. Alright, then until time t, the upper car has lost some mass. What is that mass? It is beta times t. So this is the missing mass for the upper car. And the lower car has gained the same mass, has gained the same mass. What is that mass? Beta times t. So total momentum at time t will be, upper car has a mass now less than m1 by this much, m1 minus beta times t, but now it is still moving at velocity v1. So this is a critical point. Upper car does not lose or gain speed because the sand is flowing vertically down. Here is the critical word. Vertical. The sand is not thrown at a certain angle other than the vertical direction. So that the car does not gain. If the sand, for example, if the sand were, instead of a vertical fall, if the sand is thrown at this angle, of course it would make the upper car a bit slower. Or if it were thrown backward, it would cause the car a gain of velocity. But neither is occurring here. It is flowing vertically down, so that there is no change in the velocity of the upper car. However, since the particles having some velocity already are falling into the lower car slowly starts to move because of the gained momentum. So that's why we will find this final velocity Vv2 or V of t. So at time t, from the beginning, the upper car has lost some mass by this much, m1 minus beta t. Again, let me repeat, beta corresponds to so many kilograms per second. It is the rate of flowing sand, time rate of flow. So m1 minus beta t times still the same velocity v1 plus lower car. But lower car is now a bit more massive. What is that change? Let me write it maybe in a better way. Beta t is lost for the upper car, but is gained for the lower car. So beta t until the time t from the beginning at a rate beta is lost. Is the lost mass for the upper car, which is sending it away, and it is the gained mass for the car, lower one, which is taking it, and multiplied by the unknown velocity, and this equals totally initial momentum m1 v1, and it is easy to find v2 from this. So if you open the parentheses, let's open the parentheses, m1 v1 minus beta t v1 plus m2 e2 plus beta t v2, beta t V2 corresponds to or is equal to M1 V1. So M1 V must be cancelled, and we are interested in this V2. So that V2 at time t rather, because V2 is also continuously changing as new and new sand particles are falling in it. So V2 of t at time t will be beta t, take it to the other side, beta t V1 divided by M2 plus beta t. Or let me write t separately, t beta times V1. So this is multiplied by t is a better representation. So this is the velocity. As we see from the result, as t gets larger, as time goes on, V2 will be slightly faster and faster until all the sand is finished. For example, this problem could be given in a different way, maybe. For example, the empty masses of the cars can be given, M0 for instance, and the mass of the sand, MS, can be also given, together with the rate of falling beta, and maybe it says, find the final velocity of this car, greatest value, because it reaches the greatest value of velocity when all the sand has fallen into it. And we can find the time at which all the sand particles are in the lower car. Now in this part of the lecture, let's be interested to some extent with the rocket motion, because rockets were always skipped in Physics 101, for instance, because of the changing mass. Now let's at least try to see the basics of rockets, the motion in general. Alright, this problem is not specifically convenient for real rockets, because real rockets are of course much more complex structures. This is just the basic idea that we see now. But it is not related only with the real rockets, because if you have as in the previous example, for instance, if you have a vehicle, if you are on a lorry or on a railway car, but filled with some, let's say, kind of balls or stones or sand, water, whatever, which can be thrown away. So this object, the car, railway car for example, is, let's say, maybe moving at the beginning with some velocity, and it has an initial mass. But as you throw away some of the objects inside at a certain rate of exhaust, then this system, the car with the remaining sand or remaining water, will gain some additional velocity because of this backward throwing, as we see now. So let's consider a basic, very simple rocket, but in free space. It is not on the ground, it is already fired. Let's consider a rocket. Let us consider a simple rocket moving in free space. In free space where F external is necessarily zero. There is no gravity or any other kind of external force acting on the system, so that we can conserve linear momentum. And let me draw a simple picture for this. So this is the rocket moving, rocket of mass m, moving initially at velocity, not initially because it is at some time t. This is, let's say, at time t. At time t we have a rocket of total mass m together with the fuel still inside, because until its launch from the ground, some time has already elapsed. and there is no force acting on the system right now at time t. It is moving in free space with a velocity v according to an observer on an inertial system, an observer in an inertial frame, such as a distant star, for instance. So that observer measures the velocity of this object as v, and assume it is only moving in one direction, but it has a mass m. Meanwhile, it starts to send away from its back some fuel in the negative x direction. If this is our positive x-axis, then in the negative x direction, some fuel will be thrown backward. Meanwhile, it starts to exhaust some fuel. This fuel doesn't have to be really some object which can give some energy. Just some pieces of particles are sent from the rocket in the negative direction, negative x direction. If they are thrown necessarily along the same line, minus x direction, then of course it gains some speed, loses some mass, but gains some speed in the same x-axis. However, if this fuel sent backward is sent at a certain angle with respect to the x-axis, then of course the rocket will change the orientation in the opposite sense, obviously. And if this is thrown a bit upward, then it will change orientation downward, vice versa. That's how the directions of rockets are changed, by playing with the adjusting the direction of exhaust velocity for the fuel. The orientation of the rocket can be changed. All right. Now we will compare the two momenta, linear momentum at time t and at time a bit later, t plus dt. At time t, meanwhile, it starts to exhaust some fuel in minus x direction. But let's write the mass of the fuel and velocity with respect to the rocket. These are the important parameters. Assume that a small amount dmf fuel, a small amount dmf of fuel is sent back at velocity minus u with respect to the rocket. At velocity negative u with respect to the rocket. So if you are an observer, if you are one of the astronauts here, for instance, you measure this speed as minus u. Minus because of the direction, little u is the magnitude of the exhaust velocity. So we will compare the two momenta. The momentum is conserved, which means p of time at time t will be p at time t plus dt. But during that small time interval, during the interval between t and t plus dt, this fuel, that small mass, is thrown away. DMF is exhausted, and at this velocity with respect to the rocket, so that we will conserve the momentum. P of t, what is it? It is just the initial, at time t, mass and times velocity, that's all. Mass and velocity. But at time t plus dt, just a small moment later, it is the sum of two terms. One is the momentum of the rocket with the remaining fuel, and the second part is just the fuel sent away. Therefore, the first one is, what is the mass? M minus the M fuel, because some little amount is lost. So the rocket now has a bit less mass than the time t. Time, what is the velocity? We expect its velocity to be a bit larger, v plus dv. We don't know the amount dv, but it is obvious that it will be a bit faster. Plus the contribution from the fuel sent back. What is the mass? It is the mf. What is the velocity of this fuel with respect to the outside inertial observer? It is the velocity of the rocket minus u. So it is at v minus u. So please note that v minus u is in fact a negative term, because u necessarily is greater than, maybe much greater than, the speed of the rocket. Maybe this difference is like 1 minus 4, for example. So necessarily u is greater than v numerically. So this subtraction is a negative number. However, we write it this way because v is in the positive x direction, u is in the negative x. So this has to be the way of writing it. Next, we simply open up the parentheses. So on the left we have mv, because we have this equation, m times v on the left. On the right, let's open these parentheses and see whether there's a cancellation. So if you write the first parentheses, we have m times v plus m dv minus v dmf minus v dmf and minus dmf dv. Continue with the lower term plus v dmf and minus u dmf. As we see, there is a cancellation. First of all, we have, you can cancel these, take it to the other side, so they cancel. There is one other elimination, because this term, as in all kinds of physics problems, is eliminated, is nothing almost, because if you multiply an infinitesimally small number by another infinitesimally small number, the product is necessarily totally negligible, so that this product is just zero. Because in other cases we have one very small quantity but multiplied by a normal quantity, v. It is not dv, it is dv, we would cancel that one also. So these cases are remaining, these terms are remaining. However, the product of two very small numbers is also very small number, therefore it is totally negligible. Then we are left with what? 0 on the left. 0 equals m dv minus v dmf. V dmf and plus v dmf, these also cancel each other. So we are left with only these two terms. Remaining terms are m dv and minus u dmf. So dv, for instance, dv is equal to, let's take it to the other side, dmf over m multiplied by u. But dmf was the mass of the fuel. It's a positive particle, so we have to write it as negative. A gain for fuel means a loss for the rocket. So dmf is equal to minus dm, which means gain for fuel means loss for rocket. So this is the main idea. Therefore, these have opposite signs algebraically. So now let's put this minus dm here. So we are left with dv becomes negative dm over m multiplied by u. So it's easy to take this integral because integrating now both sides, integrating both sides, but the limits, what are the limits? This may start from a certain initial value, let's say v0, until its current value v, and this may start from an initial mass m0 to the current value of m. If you take the, and u is a constant, u is not a variable in this case because the fuel is thrown away with respect to the rocket only at constant speed, so that this is not a variable. However, v and m are. So integrating both sides, we have v between v0 and v. On the right we have a negative sign, u constant, and it is ln m between m0 and m. So if you take the limits, this becomes v minus v0, that becomes minus u ln m over m0. But since m over m0 is less than 1, so ln of a number less than 1 is negative, so let's change the order, turn it upside down, so that v, take v0 also to the other side, v0 plus u times ln m0 over m. And m0 over m is necessarily greater than 1, because m0 is the initial value just at the beginning. So as time goes on, new fuels are sent back so that the remaining mass is of course less than m0. So this fraction is greater than 1. ln of something greater than 1 is positive. So obviously v is greater than, we understand that v is greater than v0 because we have to add something in this equation to v0, and v becomes the speed at the time t later. This, for example, some problems are based on the idea that in addition to the structural mass of a rocket without any fuel, some fuel is added. Therefore, total mass increases. But in time, as the fuel is sent back, only the structure remains, and that structure, without any fuel left over, gains the maximum speed. And that maximum speed can be found from this, for instance. But normally, real rockets are made, as we know, in blocks. So that part, for example, in cascades, some first stage of the rocket is thrown back, for example, together with its own structure. So as the fuel is leaving the system, its stage is totally leaving, so that during the whole motion, total trip, the stages are leaving the rocket. So at the end, only the structural mass remains. But this idea is not limited only to rockets, because as in the previous example where we had two railway cars, as some fuel is thrown, but in the previous case, if you compare the previous example with the rocket in this problem, there is a slight difference, and it is important because in the case of this railway car, the sand was falling down, but the sand wasn't exhausted backward or forward. So this is the reason why the velocity of the upper car remained the same. However, in this case of the rocket, since the fuel is thrown in the axis of motion, the velocity of the rocket changes. In the case of the railway cars, the sand is thrown at an angle perpendicular to the axis of motion, velocity for the system, so that horizontally there is neither a gain nor a loss in velocity in the railway car. But for the case of the rocket, it is not the same situation. So velocity increases by some small amount dv. And at the end, you necessarily should take this integration between some initial value and the current value. This is not the final one. This is the current value at time t. A bit later on, maybe, because this m is a variable. Remember, m represents the structural mass of the rocket together with the remaining fuel in it. Yet, as new fuel is left outside, is thrown away, then this m decreases. As this m decreases, this ratio, m0 is a fixed number at the beginning. Let me write a comment here finally. Comment. As new fuel is exhausted, as new fuel is exhausted, as long as there's some fuel to send away, as new fuel is exhausted, m in this denominator, m decreases. But m0 is a fixed number, it doesn't change, so this ratio, m0 over m, increases. V0 is the initial value at the beginning of this process, so it's also a constant, but U is also a constant. It is the rate of throwing the fuel backward. So as this ratio increases, ln of an increasing fraction also increases, multiplied by a constant, added by a constant, then V, of course, V also increases until all the fuel is sent away. And this is the moment at which the rocket reaches its maximum speed.